All right, so we are going to finish for sure 15.6 today. And 15.6 is a short section. It's about surface area. You've actually had some experience with surface area in Calc 1, kind of towards the end of Calc 1. And so just a reminder there's not going to be a lot that's the same about it, but we did things like we have this curve on the left of y equals x squared from x equals 1 to 2, and then you imagine things like revolving about the y-axis. And then you would have this 3D figure in your mind. You didn't actually have that third dimension at your disposal. We're just kind of imagining this in the xy plane. And it turns out you could find the surface area of that without the top and the bottom. And the formula looked like that. And it had some things in it, like the derivative of y with respect to x. And these integrals ended up being kind of a pain a lot of the time. So anyway, hopefully that doesn't stir up a lot of bad memories or whatnot. But I mean, you've had some experience with areas. So one thing to notice here is that because we're revolving that curve, we don't actually have that third dimension at our full disposal, that this is kind of a contrived thing. We have automatic symmetry there about the revolution axis, right? So with multivariate, it's really nice. We're going to be able to handle the surface area of shapes or 3D figures that can be more complicated. It doesn't have to have this symmetry. And it's going to be more elegant. It's not going to be kind of a, there's a formulation, but it's not going to be quite as bad. So when we have double integrals that are disposable, we're able to, they're preferred in probably whatever you study because they're simpler when you have that dimension at your disposal, extra dimension. So that's kind of a theme we've seen in the last few sections here. So here we are in multivariate land, and we're going to have a double integral. And I'm going to kind of talk about the derivation of this, but I'm actually not going to do everything that's needed to talk about it completely. Your book does a pretty good job, so just if you're interested, you can check that out. For now, just check out the fact that this formula, which I'll give you, kind of looks similar to the one from Calc 1. But we have a partial with respect to x, partial with respect to y, still have the plus 1 in the root, and it's a double integral. So the idea here is we have this image there that is going to show us sort of what's happening here and where that formula comes from. And that is we have our surface there. Z is a function of x and y as was shown. And for each of our approximating boxes, we're going to call that R sub ij. So this is sort of like your quiz where you have that elevation map. You have that grid, right? And you're estimating the Z specifically in those to find the average Z overall. So here specifically what we're trying to get at, however, is surface area of a surface like the blue one here. And so kind of the same concept there, but what we're going to imagine is projecting up our individual approximating domains in the XY space, those subdomains, up to the surface. And then instead of having the entire surface characterized for that projected domain, subdomain, we're just going to do a linear approximation for that and make it a tile. Because we're taking the limit of this. So all this is going to condense down on every single point on the surface, which right kind of blows your mind, right, to think about. But you know, so we have these approximating tiles. They are going to be in the shape of a parallelogram. And if we do the limit to get our exact integral, then that'll be an exact representation. So back from our vector work, we can define that area, that parallelogram with a cross product. And we're trying to get the magnitude, which is dependent on delta A. And so we can get an exact representation in that way. So I'm really super glossing that over. If you want some more details, you can look at your book. But basically the idea is we have a linear approximation of the surface on each subdomain interval. And then we're characterizing that with a cross product's magnitude. And then we're doing the limit things to make it a integral and do it exactly. And that's what that formula is. All right, let's use it. So example 1 says calculate the surface area of the portion of the plane x plus y plus z equals 3 in the first octant. So this is actually one that's not too difficult to graph. You can use intercepts, x equals 0, y equals 0, and z equals 0 one at a time. And then, or I should say x and y at one time to find the z intercept. So 2 at a time, letting them equal 0 to find the third one, and then you can get those x, y, z intercepts, and then the plane is going to be characterized by that. So you're going to be given this formula. It's a double integral, and our domain here is over the xy plane. So if it's not a rectangle, then you have to use variable bounds. It's something we've learned. If it's a rectangle, then you're just going to have numbers in for the little numbers next to the integral. If your domain that projects onto the xy plane is some sort of rectangle. Okay, but that's not what we got. What's the shape of the domain in the xy plane? So imagine just the xy plane. It's the first octant, so it doesn't go beyond that. Starts with a T. Called a triangle, right? Okay. And so just like hopefully you discovered on this homework that was due today, is it useful to graph the domain in the xy plane to figure out your limits of integration? All right, so keep doing it. It's helpful here. So this is what it looks like. Reminder that this is just a line with this triangle that's defining this hypotenuse thing here. And so some of you are not writing that equation of line correctly. That should be fairly straightforward. Lots of things to do that you can do there. You automatically have 2 points on the line that you could substitute in finding the slope here, rise over run. So make sure you're doing that correctly. It's just the equation of line like you learned in high school. So having that visual is helpful. Okay, now maybe looking back at the integral and seeing all the stuff that needs to go in there. So notice that we have f sub x as part of that, and f sub y, and that's of our equation up here. So first thing you need to do is solve for z, because this equation here, or this formula is assuming that you have z as a function of x and y. And that's easy to do. We just move over the x and the y by subtracting them, right? And then we can find our f sub x and our f sub y. So they turn out to be very simple, -1 and -1. And we're going to be able to plug those in now to this formula. Also, we need our bounds, which is what we started working on by graphing the domain. And you could do this either way, but it's probably going to be in the situation where you're going to write the equation y in terms of x, because that's what's a little bit more familiar. So then the variable bounds would be in terms of y, and y, looking from the least to the greatest, would be the line y equals 0 up to the curve y equals 3 minus x for any particular x. So that defines our domain. And then x is left to define, and then that's in terms just of constant bounds. So the extent of x is from left to right, that our domain goes from 0 to 3. So any questions about where we're at right there? So we just set it up. Kind of similar to Calc 1 in that once you get that integral set up, then it's like, okay, just do the integral, right? Fortunately, this is an easy integral. It ends up just being the square root of 3. And so, by the way, can I just switch the limits of integration and do like 3 minus x, have that integration with respect to y go on the outside? Can I do that? No, you can't do that. When you have variable bounds, they have to stay inside the variable bounds for which they're defined in terms of. I think I said that right, but it probably didn't make any sense. So 3 minus x, in other words, it has an x in it. And you still got to integrate with respect to x on that thing, or it doesn't work. So notice that the dx is on the outside. It's got to stay there. Okay, so anyway, the integral of square root of 3 with respect to y is just square root of 3y. And then we plug in, as usual. This one ends up still not being so nasty, which is nice. Sometimes it gets real, blows up right there. And so then we just have 3 minus x, which is an easy integral in terms of x as well. So that's nice. Just plug and chug, and we get a numeric answer that we leave in exact form. So any questions about that one?